Hello everyone, myself Syed Hussain, Assistant Professor from EEE Department in KJDT College of Engineering and Technology. So today, working principle of transformers. So basically, in all electrical machines, only one working principle is going to be operated, and that principle is Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. So based on these principles only, all electrical machines are working in this generation. Okay. If you look at this principle, basically the Michael Faraday is the greatest scientist. He discovered that whenever a conductor is placed in a magnetic field, the conductor will cut the flux across it and EMF will be induced in that conductor. Okay, that means the Faraday has discovered that there is some kind of EMF has induced in conductor when it is placed in some kind of magnetic field. Okay, until and unless the EMF will not be induced in that conductor. Is it clear? So, for example, I am going to consider a magnetic system that having that North Pole and South Pole. So obviously the flux will be exist between the two poles, right? So those are the unlike poles. So obviously some kind of magnetic flux will be established between these two poles. So these lines represents magnetic flux lines. These lines represents the magnetic flux lines. So guys, now according to Faraday's law, I need to keep one conductor. Okay, I need to keep a length of conductor between the two poles. So I am going to consider here a length of conductor like this. Okay, this is particular length. So we can call it is a small l. This is the length of that conductor. Okay, now this conductor has to rotate. Between this magnetic field system, so that only the EMF will be induced in that conductor. Until and unless the EMF will not be induced. Why? Because there should be some relative motion. As we have seen in the last session, there should be three requirements. For getting the EMF in the conductor. What are the three requirements? First one is a set of conductors. Second one is a magnetic field system. Third one is a relative motion between the two. That means set of conductors and the magnetic field system, isn't it? So this conductor has to rotate. By means of a prime mover or diesel engine. Okay. Now you can see here, sir, with a single line you are representing a conductor. How can I understand? Instead of taking a single conductor, you just take a single turn. Rotate this conductor. This is for assumption purpose. Basically here, this is a single conductor and this line also represents a single conductor. But in the practical, we have a bunch of conductors, right? That bunch of conductors cannot be placed here, right? On the board we cannot represent the bunch of conductors. So we can consider only one single conductor. That conductor I have represented here. Is it clear? Now whenever this conductor is rotated under the field, under this magnetic field, this conductor will cut the flux. How it will cut the flux? The rotation having the 360 degrees. Okay. So during the 0 to 90 degrees position will be different, and 90 to 180 degrees the position will be different, and in the similar manner 180 to 270 and 270 to 360 the positions will be different for each and every angle. Okay, is it clear? Now if you see here, whenever this conductor perpendicular to the magnetic field system, whenever this conductor is perpendicular to the magnetic field system, the EMF will be induced in the conductor. That means the total flux lines will cut by this conductor. Okay. So now whenever this conductor is parallelly moving to with respect to field system, there will be no EMF. There will be no EMF. So every time I am saying that EMF will be induced, how it is represented? How it is represented means that can be represented by small e BLV sin theta. BLV sin theta. This is the EMF equation. This is the EMF equation of particular machine. Okay, and that machine consists of the magnetic field system and a length of a conductor. Now, if you look at this, the B represents what? Magnetic flux density, magnetic field density, and length represents the length of the conductor, and the V represent how much velocity the conductor has to be motion. And what is the theta here? It is a new thing here, right? The theta means it is a deflecting angle. So the angle that has to be occurred between this magnetic field system and this rotation. Okay. Now, according to this statement, whenever the conductor is perpendicular to this field, the conductor will cut the flux, right? So that EMF will be maximum here. EMF that will be induced in the conductor will be maximum. Okay. The same conductor, when it is moving parallel to the magnetic field system, the same EMF will get 0. Okay. It will be the 0 here. Now, is it clear? Right. So, this is how the Faradays has explained in detail. Now, if you see guys, here the conductor has to be moving with some velocity and EMF has been induced. Whenever this conductor has placed on the stationary and the field has to be moving condition, how the EMF will be induced, that is the case we are going to see here. Okay. Now, in this case, the conductor is rotating with some kind of velocity and the field system has been stationary. Is it clear? So, let me write here. Let me write. The field is stationary here and the conductor and moving. Now, can anyone tell me what kind of EMF can be induced in this conductor? What type of EMF is going to be induced in this conductor? What type of EMF it is? Yes, exactly. So, the type of EMF which is induced in this conductor, that is dynamically induced EMF. Dynamically induced EMF. Is it clear? The EMF which is induced in this conductor, that is the dynamically induced EMF. Now, I said that now I am going to place the conductors as a stationary and the field has to move. Okay. Now, for what condition we are going to take one iron piece. Okay. I am going to consider one iron piece here. On this I am going to take winding here. I am going to take a winding on this iron piece. This is to be like this. Okay. And this winding is excited by an external source. This winding has to be excited with an additional source. Now, this is an AC supply, guys. This is an AC supply, and this is the winding here which I have wounded like a spring. Okay. This is just like a piece of iron. Simply we can call the solenoid. right. Now, if you look at this, what I said in the before, it is exactly matching with this. The winding is stationary, the winding is stationary. Now, on this winding which is excited with some supply, right. So, when it is excited with the supply, the current will pass through this winding, the current will pass through this winding. So, obviously the current will passes throughout this winding, right. So, according to Faraday's laws of electromagnetic induction, okay, conductors are existed, the supply is there. So, that means the conductor is carrying some current, right. So, whenever the current is carrying by some conductor, there will be possibility of magnetic flux develop, right. So, some kind of magnetic flux will be established across this winding. How? In which direction the flux is established across this winding? So, let me tell you one thing, there is one rule, So, we can use the two rules here, one is a right hand thumb rule, or corkscrew rule. With the help of these two, we can find the direction of flux, or else we can find out the direction of current also. Okay, with the help of these two rules. Let me tell you one thing, just consider a conductor, a straight conductor here, okay, and the current is passing through this conductor I. The current passing through this conductor is I. Now, as I said that whenever the conductor is carrying some kind of current, whether it may be a 5 ampere, 10 ampere, whatever it is, whenever carrying some current, the flux will be established across this current, across this winding. In which direction it is? For that only the right hand thumb rule can be used here. So, the right hand thumb rule, that is explained that the direction of current, use your right hand, the direction of current can be represented by thumb in upward direction, the orientation of fingers, that will represent the direction of magnetic flux, okay, the direction of magnetic flux. Is it clear? So, now I am drawing here the direction of flux lines, So, how it is to be? Guys? It is in the inwards, okay, it is inside. So, the direction of the flux will be like this, that is we can call the right hand thumb rule. Now, in the similar manner, I am going to consider the current is passing in the downwards direction, Now, tell me how the flux line's direction will be. Either it is in the clockwise direction or an anti-clockwise direction. Yes, exactly guys. So, it is to be clockwise direction. Why clockwise direction? Now, what I said, just indicate the direction of the current in the thumb with respect to the thumb. So, it is in the upward direction, right, downward direction. So, you can take the downward direction like this. Now, orientation of the fingers, just open your fingers and orientation like this. Okay, what will happen? It is to be like this. So, the current direction represents the thumb and the remaining will be the flux. So, it is to be the clockwise direction. This is how to find direction of the magnetic flux lines. Now, this can be applicable here. Now, if you see here, either you can apply the thumb and you can apply the fingers for the flux, either you can use another thing. Just indicate the four fingers, these four fingers, not four finger, these are four fingers. You can use these four fingers for the direction of current and use this thumb for the direction of the flux. or you can use the direction of the current with the thumb, you can use the direction of the flux, whatever it is, depends on the requirement. Now, if you see here, the direction of current is upward, the direction of the current is upward. Okay, just I am closing the fingers. What is the direction of the flux? The thumb represent in this direction, the left side direction. So, the flux direction will be like this. Okay. So, how it will be like this? Exactly here. So, like this the flux will be established across this winding. Is it clear, guys? Is it clear? Right. Now, here according to Faraday's law, the flux is established, the conductor is placed under the field of magnetic. Now, the EMF will be induced in the conductor. So, what type of EMF it is induced? Exactly, guys, which is the statically induced EMF. It is statically induced EMF. Statically induced EMF. Okay. So, this is the dynamically induced EMF because the conductor is under motion condition, it is rotating with some velocity. Now, the conductor is stationary, the field is rotating across this conductor. Now, it is become the statically induced EMF. So, there will be some equation, right? So, we have to represent in mathematical. The most of the equations should be in the mathematical model only. So, in our electrical department, imagination is different. That imagination should be matched with the equations. Is it clear? Now, here, according to Faraday's second law, E can be represented by N into d pi by dt. This is the Faraday's second law. Why I have taken this equation means, the Faraday's second law states that the magnitude of induced EMF is directly proportional to the rate of change of flux linkages. So, the N pi which represents the rate of change of flux linkages, guys, flux linkages. Okay. So, that the E can be taken as d by dt of N pi. So, the E can be taken d pi by dt like this. Okay. So, now here one thing you need to remember, that there should be a negative sign, in this Faraday's second law. So, this represents Lenz's law, the negative represents Lenz's law. According to Lenz's law, the magnitude of EMF which opposes the total supply voltage, Okay, guys, I hope it is very clear. You guys understand about the dynamically induced EMF and the statically induced EMF, and we can find out the direction of the magnetic flux with the help of right hand thumb rule or corkscrew rule. Okay, guys, thank you everyone.